Today we want to talk about the dot product, how to calculate it, what it represents, most importantly, how we think about it. The way we want to think about the dot product is we want to think about the dot product as multiplication at an angle. The dot product is multiplication at an angle. The dot product is an inner product, which means it's going to produce a scalar. The dot product is going to take two vectors, multiply them together, and produce a scalar. So the dot product is a scalar product. The reason we call it dot product is because we use a dot to indicate the multiplication. So what do I mean when I talk about multiplication at an angle? Let's suppose that I want to multiply 2 times 5. When we're multiplying regular numbers, if I say 2 times 5, that's 10, right? Yeah, 10. 2 5s is 10. Because the 2 and the 5 are both scalars, there's no direction associated with them. There's no direction associated with 2 times 5. It's we take all the 5 and we make 2 copies of it. We get all 5 from both the copies. But what if we have our multiplication at some funky angle? Let's suppose that I have a 2, my 2, I don't know why I'm making it so small. So here I have a magnitude of 2. I'm going to multiply this 2 by a 5, but the 5 is not going to be going in the same direction as the 2. 5 is not going to go in the same direction as the 2. I'm going to put the 5 in the direction of 3, say 4. So instead of my 5 going in the same direction as the 2, this is my 5. I'm going to name these vectors. It's going to come up later. So here's my vector v, which is 2i plus 0j. The magnitude of v is 2. The other vector, I will call u. Is going at 1, 2, 3, 4i plus 3j. So the magnitude of u is 5. Because I have a 3, 4, 5 triangle. So the length of u is 5. I just find, okay, I take the square root of the sum of the squares of the lengths. Yes. Yeah, I guess my I and J should have little hats. Might rain today. In our first example, when we just had scalars, 2 times 5 was 10 because all the 5 was going in the same direction as the 2. They're both going the same way, the same direction, so we just multiply. But in our vector case, not all of the u vector is going in the same direction as the v vector. Only parts of the u vector is in the same direction as the v vector. How much of the u vector is in the v direction? Here's our horizontal component of u. That's 4i and 0j. The magnitude of the horizontal component is 4. And then I have the vertical components of the u vector. That's where the 3, that's what gives it this upward angle. And the magnitude of the u vertical is equal to just 3. So when I think about the dot product of u dot v, I want to think about multiplying these magnitudes, but not all of one vector is going in the same direction as the other vector. Even though the magnitude of the vector u is 5, the only part of u that's going in the same direction as v is 4. So here we would expect u dot v to equal just 2 times 4, or 8. Because that's the only part of the u vector going in the v direction. Any questions? Notice that I have not told you how to calculate the dot product. So some of you who already know how to calculate the dot product have done so, and it's like, ah, yes, that checks out. I can see where those zeros are going to come in, specifically this 0j. So what we're going to find is that u dot v, in this case, u dot v is equal to 8. Because there's only 4 of the vector u is going in the same direction as the vector v. This is how we want to think about the dot product. I'm multiplying two values, but if those values have different directions, then I have to look at how much of one vector is going in the direction of the other vector. We only get to take how much one vector is going in the direction of the other vector. In our first example, 2 times 5 is 10. 2 and 5, full scalars, no direction. They just multiply together. Any questions? This is the thinking of dot product. Multiplication at an angle. That's the thinking of the dot product. Let's talk about calculating the dot product. Let's first start off with how we define the dot product with this multiplication at an angle thinking. U dot V is the magnitude of U times the magnitude of V. And then we're going to be limited by some factor. So the dot product is U dot V is the magnitude of U times the magnitude of V times the cosine of the angle between the vectors. U dot V is the magnitude of U times the magnitude of V times the cosine of the angle between the vectors. Specifically, the shorter angle between the two vectors. We've got two vectors. There's going to be two different angles between them. One will be between 0 and 180. The other one will be between 180 and 360. We want small. Theta is some angle between 0 and 180 degrees. I'm writing it in degrees. I have a trig class this semester, so I'm going to be writing angles in degrees. Eventually, I'm going to forget to switch my calculator back to radians and stuff can break, but it's fine. Another way to calculate U dot V is the sum of the products of the corresponding components. We can also calculate U dot V as the sum of the products of the corresponding components. Sum of the products of the corresponding components. So if U is the vector U1, U2, U3, and V is the vector V1, V2, V3, then U dot V is U1, V1 plus U2, V2 plus U3, V3. I just moved this up into R3. If it's in R2, just drop that one off. So in our previous example where U was 4i plus 3j, and V was 2i plus 0j, we get U dot V is 4 times 2 plus 3 times 0. There we see that 2i plus 0j. There we see that no vertical stuff in the vector V, taking away all the vertical stuff in the vector U in the product. Any questions? How's everybody okay? Everybody looks so stoked. You all look like this.
It's the face of acceptance.
Acceptance. That's all we need to go for. It doesn't have to be awesome all the time. I like evolutionary standards. Good enough. So I'm going to, let's practice operations on vectors. We need some vectors. So I need to define some vectors. Here are four vectors. So here are four vectors. And in each of these problems, I want you to perform these operations. Because this class is not awkward enough, we need to make it more awkward. You can probably guess what's going to be happening in a moment. We got 2, 5, 8, 11, 15, 19, 23, 26, 29, 32.
That's the red down.
Take one and have that cross. All right, so here are 4 vectors, and here are what, 12 things to do with these vectors. You should also have in your possession a card labeled ace through 8 as the number of people. I got the 9s and 10s. And you'll notice that the 10 boards in this room are labeled ace through 10. So they each all have a pen. I want you to make these calculations. If you want to do, I want you to take 3 minutes, get started on these calculations. Once you have these calculations, I want you to meet with the people would have the same card. So everybody with the card 9 will go over to the 9 board. And you will double check to make sure that your calculations are correct at step 1 and step 2. You will note if there's anything interesting that happened in the calculations. How can you interpret these results in the case of thinking about dot product as multiplication at an angle? So take a few minutes, work on these problems, then gather in your groups, and I'll come around and check. Things you will not do. You will not steal my cards, even though they're cool and they have constellations on them. And you'll also not steal my pens. They don't fit air tags, so I can't hunt you down. All right, at this point, switch from individual to teams. Go to the board corresponding to the card that you received. Introduce yourselves if you have not done so already. And check your work.